Welcome to Physics and Philosophy. In these videos, we shall be looking at philosophy and its impact on quantum physics. Unfortunately, philosophy has been purged from much of the curriculum of modern physics, and we think that's a mistake. We're going to examine the role of philosophy by looking at the contribution of three philosophers in particular. The first of these three philosophers is Karl Popper. Popper claimed that to be scientific, a theory had to be falsifiable. That is, it had to be testable against the real world and potentially shown to be false. If it's not falsifiable, it's not a scientific theory. That seems like common sense, but a lot of modern physics is replete with stuff that's not observable or testable, or is ever likely to be. Examples include multiple universes, microscopic wormholes connecting particles, particle trajectories, and of course, the great granddaddy of fantasy physics, string theory. Strings are not directly falsifiable. In addition, modern string theory relies on supersymmetry. Supersymmetry predicts partner particles for the particles we know about. They are notable by their absence from particle colliders. Arguably, string theory has already been proven false. Abandonment of falsification has led to a position where physicists seem to believe they can choose whatever interpretation or theory they feel like. However, physics is not primary school. Not everyone gets a prize. Not all theories are the same. The second of our philosophers, Thomas Kuhn, came along after Popper, and he said science, including physics, is a social endeavour. For example, falsifiability is not applied consistently. A classic example is the perihelion Mercury. For 200 years, Newtonian mechanics correctly predicted everything from cannonballs to the trajectory of comets. No one doubted its correctness, except it did not predict the advance of the perihelion of Mercury. To explain the discrepancy, scientists from the 1860s onwards theorized the existence of another planet called Vulcan, close to the Sun, and therefore hard to see, which was responsible for the slight advance in Mercury's orbit. Of course, it did not exist. The resolution of the mystery required the general theory of relativity. By rights, Newtonian physics had been falsified in the late 1800s, but no one took that proposition seriously. Kuhn also says that science advances in fits and starts. A single framework called a paradigm is developed. Paradigms are not challenged for extended periods of time by most of the scientists who use them to solve day-to-day problems. Newtonian physics is a paradigm. It's unchallenged for about 250 years. Other paradigms include Maxwell's equation, special relativity, general relativity, quantum mechanics, and the Standard Model. String theory is also a paradigm. Kuhn provides some wriggle room regarding falsification and other criteria for assessing theories. We'll have more to say about that later. Moving on, quantum mechanics seeks to be a theory of everything. But what should that look like? There is a halting problem. What should the fundamental building blocks look like? If we explain everything in terms of X, should we then seek to explain X in terms of something else? Actually, classical Western philosophy has something to say. We look to the works of Immanuel Kant, the third of our philosophers. Immanuel Kant said, "We know the world through our senses, and from that information construct mental models to understand and predict our interactions with the external world. The Kantian worldview can be represented by the following diagram. The left-hand side represents the external world. Only that part of the external world that interacts with the person's senses is observable. The rest of the universe is utterly unknowable. The senses sit on the boundary between a person's self and the external universe, and the self contains the mental models used to understand the universe." The Copenhagen worldview, primarily created by Bohr but based on the work of Kant, can be represented by this diagram. The similarity is not accidental. Senses are replaced by measuring devices. Consciousness is replaced by intelligence, could be a robot, for example. The self is replaced by an observer. Copenhagen measurements are elements of reality, to use Einstein's terminology. The waveform is not. That it is a mental construct. Schrodinger's cat
for example, does not represent an issue for Copenhagen. Its measured state is simply unknown. The waveform represents the cat in a state in which the cat is half alive and half dead. But that's okay, because it's not real and it represents our knowledge of the cat. Instantaneous collapse of the waveform also does not present an issue, as the waveform is not real, so it's not subject to any relativistic constraints. Copenhagen provides a way to understand the transition from the quantum world to the classical world as well. This diagram shows three panes. The left-hand side pane shows what we know about the particle moving left to right. The measurements are elements of reality and shown in this pane. The center pane shows the mental models of quantum mechanics fitted over the measurements. The right-hand side pane shows mental models for the classical mechanics fitted over the measurements. It's up to the observer to decide which mental models to use. A more graphic example of Kuhn's paradigms is harder to imagine. So why have so many physicists abandoned falsifiability? Kuhn stated that science is a social enterprise. It is therefore also a commercial enterprise. There have been no real advances in the arena of fundamental theoretical physics since the Standard Model in the 1970s. But PhDs and universities rely on publications of new papers for funding. The media is always interested in consuming a good physics story as well. The only way to do that is to loosen the requirements for a paper to be regarded as scientific rather than speculative. String theory in particular is tremendously complex and capable of generating thousands of papers. It's also infinitely modifiable. If a predicted particle fails to appear, then internal parameters can be adjusted so that the predicted particle is just outside the range of energies tested by the current crop of particle accelerators. The theory cannot be killed. It is undead. The theory that refuses to die. In the following videos, we shall be exploring the Copenhagen family of worldviews further and introducing a slightly modified version of Copenhagen called the ticker tape interpretation. Hope to see you soon.